This is video 2 of our lesson on finding geometric volume of solids of revolution or solids of rotation. So we're just going to do example 1 in this one. Notice in this one it says, for each of the following, set up the integral that can be used to find the volume of the solid of revolution described. And then this says you may use your calculator to evaluate the problem in integral, or the integral in problem 3 only. I think we will go ahead and do these mostly with the calculator, but at least for the first 2, we'll go ahead and do it by hand, just because I think it's good for you to remember how to do these by hand and to see how you would take these problems to completion if you did them by hand. Okay, so problem number 1 says we're going to use integration to find the volume of the solid generated when the line y equals x for x between 1 and 4 is revolved through 2 pi. So what that means is we're going to take this piece of the graph and we're going to rotate it 2 pi, meaning a full circular rotation around the x-axis. Okay? All right, so let's draw a graph of this first, figure out what's going on. So if we look at the line y equals x, it looks like this. Right, but this says we only want the portion of the graph for x between 1 and 4. So if we imagine that right here, here's where x is 1, here's where x is 4. Oops. We only want that part of the graph. So I'm going to get rid of this entire line and we'll just draw this portion of it right here, between here and here. Right, and we're going to rotate that around the x-axis. So again, just imagine taking this piece, you might have to imagine it kind of attached to the x-axis with little wires or something like that, because it has to stay that distance away from the x-axis. And you're going to rotate it around. So you're just going to rotate it 180 degrees. Again, imagine starting with this point, bringing it up out of the paper. It's going to go in a circular path. It's going to land here, and then it's going to continue on its way. And then the same thing here with this point. We're going to take that point, rotate it up out of the paper in a circular path. It's eventually going to land over here. Its mirror image. I'm going to move that just a little bit closer to make it actually look a little more symmetric. All right, and so it's going to land here, and then it's going to continue around. So in other words, we're going to end up with these circular paths. So we're going to end up with a path here, like this circle. This point right here is going to go in a circular path. This point right here is going to go in a circular path. All right, so hopefully you can kind of imagine that three-dimensional object, especially if I put in another little piece here. You can probably kind of imagine that cylinder that's sliced in the middle. Sometimes I think if you turn your paper side or your head sideways or your paper sideways, it looks more 3D. So make an attempt to draw that. It doesn't have to be perfect. Some of you who are artistic will probably draw some beautiful pictures there. All right, so now what we want to do is take this sample cylinder that's right here and write a formula for the volume of that sample cylinder. So we know that cylinders are pi r squared h. So this is going to be pi times, and just like the last one, the radius is just going to be y, because if I picture the radius going from here to here, where these endpoints are the points x0 and xy, and notice that that y is on the line y equals x, then the radius is this distance from here to here, which is y minus 0. So that's just going to be y squared times h, and h is the height of that cylinder, which, because we're making vertical cuts, is going to be dx. So that means if we take all of the cylinders, add them all up, let the width go to 0, we get the exact volume with an integral. This becomes the integrand, pi y squared dx. So what are my x values? Because this says x, these have to be x values. My first cut is right here, and remember that's where x is equal to 1. And then my last cut is here, and remember that that's where x was equal to 4, right here. So there's our integral. Now, if you were doing this with your calculator, you probably could just leave it like that, and then just make sure that your function y equals x is in the calculator, and then that'll take care of it for you. But if you were going to do this by hand, all right, let's just continue this on. we need to get this all in terms of just x. So it becomes the integral from 1 to 4 of pi times x squared dx. All right, so then if I want to finish this up by hand, I need to do the integration. And notice that this is an integral of a constant times a function. And so you can bring that constant out in front. I'm going to move over here so I can make a little more room. So I get pi times the integral from 1 to 4 of x squared dx. So this becomes pi times, so remember now if I'm going to do this by hand, I have to take the antiderivative of this. So that's 1/3 x cubed, evaluated from 1 to 4. Technically it's this, like that. So then, if I do this evaluation, if I sub in the 4 first, so I have pi out in front, and then when I sub in the 4, I get 1/3 times 4 cubed. Remember, you take the upper one first, and then I do minus, now I sub in the 1, so 1/3 1 cubed. And so this becomes pi times 64/3 minus 1/3, which is pi times 63/3, which is 21 pi. Now because it's volume, this would be cubic units of some kind usually. But again, unless we know what the units are on these axes, you know, if this was seconds and this was square seconds for some reason, I don't know why it would be that, but if it was, then your volume would be cubic seconds, all right? It would be this times this. That's a really silly unit, but we don't really know what the units are, so that's why I'm not really fussy about you putting units here. So just 21 pi is fine. Now, on this one, I do want to point out that we could find this volume geometrically because this is a truncated cone. So remember that this continues on to here. And so what we have is basically a cone like this with the tip cut off. It's actually called a frustrum. Is this piece right here. And remember that a volume of a cone is 1/3 pi r squared h. And so we could actually find the volume of this frustrum geometrically and compare and see what we get. So notice that this is going to be, the volume is going to be the whole cylinder, which is all of this, minus the little tip. So minus the tip or minus the top. And so for the whole thing, we're going to have pi, or I'm sorry, 1/3 pi times the radius. Now remember that the radius is the radius of the base, right? And this was at x equal 4. So that means that this point is the point 4, 4 on our graph. And so the radius is this distance right here, which is the y-coordinate, which is 4. So we get pi times 4 squared times the height, right? And the height of this is also going to be 4. It's the distance from here to here. Minus, all right, and then the tip of it is just this piece that's right here. And the radius of that tip, because again, this is the point 1, 1, the radius is this distance right here, which is the y-coordinate. So this is 1/3 pi times the radius squared, which is 1, times the height, which is this distance right here, which is also 1, because the x-coordinate here is 1. And so we're going to end up with, just like we did before, 4 squared times 4 is 64, times 1/3 is 64/3 pi, minus 1/3 pi. So that ends up with 63 pi over 3, which is 21 pi. Now, we're not going to be able to check that with all of the figures because they're not all going to be geometric figures that we have formulas for. But this one we did. So that hopefully kind of convinces you that this formula works.